Hi Vasant. So guys, we'll wait for some time so that everybody joins. Amazing. You have done an EDA in Streamlit app. Very good. Hello Gautam. Hello guys. How are you all? I hope everybody is doing fine. We'll wait for some time so that everybody joins and then we can actually start, right? We'll start from 7:15. Uh, Hello everyone. Hello. Hello. Hello guys. We'll just wait for another 3 minutes, so that everybody joins. I'm also messaging every group as such so that we can actually start Discord. How was the day? Yes, it was good. Sir, in yesterday forecasting, how to convert forecasted values to original format. See, that time we were getting some original format values only, right? We can take that values and we can actually see this, right? Raghavendra Joshi, fantastic to learn from you. Thanks a lot. No problem. Okay. So in this video, we will be discussing a lot about normalization and standardization. So feature engineering series में कितना topic है? After normalization, standardization, there are some more things that we'll be discussing, and after that, we will be moving towards feature selection. Okay. Let some notification go on, and then we will start. So guys, if you really want to have the GitHub link, probably the GitHub link is given in the description. You can check it out. So the GitHub link is basically called as feature engineering live sessions. So all the materials I'll be putting it over here. Okay. And you can also see forecasting Facebook FB profit was also uploaded over here itself, right? So if you have any queries, just try to download it from here and try to work from here. Okay. All the data set has also been mentioned. So how to identify for feed scaling and transformation. I'll tell you all about that, Shailesh. Don't worry. In this video, we will try to understand everything about normalization and scaling. Okay. Yeah. So in time series, what happened if we have more than one columns? Please let me know. So it is called as multivariate analysis. Multivariate analysis on time series. Sumit says, sir, do we really use hypothesis testing for model building and performance evaluation? Is it just a hypothetical concept or used mainly in statistical modeling? They basically say that whenever they want to represent that particular information to someone, so it is the language of statistics and machine learning, where you can actually use all those things. Hari Prasad, if you're a student, go with 59 plan, otherwise go with 299 plan, guys, with respect to membership. Okay, another 1 minute and then we will start. Okay. Good evening, Chinmay. Good evening, Harsh. Khushbu Singh, thank you. Krish, you are champ. Keep rocking. Ram Mohan, hi sir. Hello Ram. Okay guys, let us start. And again, today the main aim is all about transformation of variables. Okay. So here I'm just going to say transformation of features. Okay. So why this is required? Okay, everyone. So first of all, let me make this as markdown, and probably I really want to open a notepad to make you explain much more better why transformation is required, why people actually do a lot of transformation, that we will actually be discussing here, right? So first of all, can you give me a quick yes if you are able to hear me clearly, right? Can I get a quick yes if you are able to hear me quickly? And guys, if there is any lag in the video, just reload your page. It may be due to internet connection or something else, but just reload the page. It will be perfectly fine. Okay. So here we are, why transformation of features are required. This is what we are actually going to discuss. Why transformation of features are actually required. Now guys, always remember one thing, very much simple, that there are some of the algorithms. If I take an example of some of the algorithms, right? If I take an example of, suppose, linear regression, right? In linear regression, what we do is that internally there is a concept of gradient descent, right, which will help us to find out the minima point, which is also called as a global minima. If you don't know about all these things, guys, just go and check my complete ML playlist where I have discussed about all these things. And you know that for linear regression, our main aim is basically to find out the slopes, the coefficients, right? The coefficient parameter. And really, to find out the coefficient parameter, we will be requiring gradient descent concepts, we'll be requiring global minima concepts and all. And usually to derive it pretty much faster, right? What we do transformation. I'll tell you why. Okay, I'll just tell you why in some time. Now, second, suppose if I take some example of algorithms like suppose I take an example of algorithms like KNN, that is K nearest neighbor. If you don't know about K nearest neighbor, guys, it works on Euclidean distance, right? It works on Euclidean distance. It tries to find out the nearest point, and then it will either classify them, or if you are using a regression, it will try to find out the average. Okay. We can't see what you are typing, Krish. Sonia Rajput, can you just, because I can see in my channel whatever I'm typing, I'm able to see. I'm also monitoring that in my YouTube. I can see. Just reload your page, Sonia, or just try to see that. Okay, but I think everybody is able to see what I'm actually writing, right? So algorithms like KNN, and if I take some algorithms like unsupervised machine learning, like K-means, right? K-means, this is all K-means. Then I have hierarchical clustering, right? These all are clustering algorithms. Internally in this, there's a concept of something called as Euclidean distance, right? We try to find out the distance between 2 points, right? We try to find out the distance between 2 points, and then we will be able to try to find out what is the distance, and then we'll try to group them, or then we'll try to find out the nearest neighbor. Now in this Euclidean distance, or while you're finding out the global minima, what is the problem with respect to this? See this. Suppose I have feature f1, I have feature f2, I have feature f3. Now suppose I just have feature f1 and f2, right? And suppose my feature f1 has values like 24, this has like 56, right? Or suppose my other features have values like 21, this is having 100, then I am having 45, then suppose this is 67. Like this, we have some n number of features, right? Now when we have this many number of features, always remember, guys, with respect to this values that you see, these values difference are pretty much huge, right? This difference is pretty much huge. And when this difference is pretty much huge, this Euclidean distance or finding out the global minima, because internally if I talk about gradient descent, right, there's a back propagation that is happening on some kind of equations, and if the values are actually smaller, at that time the transformation, then the global minima point can be easily found out very much quickly. And if I take an example of Euclidean distance, right, now suppose, imagine I want to find out the difference between 24 and 56. Okay, if this is my x1 x2, if I really want to find out what is the distance between these 2 points, or if I'm taking a two-dimensional point, in two-dimensional basically I'll be having some xy like this, it will be something like this. See guys, so suppose this is my x1 comma y1 value, and this value is basically represented by 24 comma 54, right? And suppose if I take another option like this, if I have another option, or if I have another point x2 comma y2, and suppose this value difference or these values are actually somewhere around like 30 comma 70. Now if I want to find out the difference between, and this is, remember that this is my point 1, okay, this is my point 1 and this is my point 2. Now if I want to find out the difference or the distance between these 2 points, I usually find out a equation like root of x2 minus x1 whole square plus y2 minus y1 whole square. Now in that case, you'll be seeing that these values are pretty much larger, right? So usually the distance is also much larger, right? So we should try to transform these variables into some scale so that, you know, this Euclidean distance should be very much minimal. Okay, Euclidean distance should be very much minimal, and then our process of calculating the Euclidean distance becomes pretty much faster. That is the main aim of transformation. We will try to scale down this value. We will try to scale down all these values. So one instance, I'll say you that I'll try to scale down this f1 and f2 feature values between 0 to 1. Okay, all the values will be scaled down between 0 to 1. Suppose if I take an example of feature 1, okay, this all values should be scaled down between 0 to 1. If I take the example of f2, then I will try to scale down this value between 0 to 1. This is one of the technique. This kind of transformation, this type of scaling is called as min-max scaling. I'll be discussing about those kind of scaling. Okay, but I hope you understood why transformation of features are required. The main reason is that whenever you want to find out the transformation of the feature, why you have to do the transformation of the feature, because your points, always remember one thing more guys, every point over here, every point, like I'll just write it down, every point has some vectors and direction. Okay, every point has some vectors and direction, and these vectors, if there is a huge difference, then probably the calculation, the transform, the finding of the gradient descent or the finding of the Euclidean distance may probably take more time. So we should try to scale down this particular value. Okay, so I hope everybody understood this. Can I get a pretty much quicker yes if you are able to understand, so that I'll move ahead? Okay, just give me a thumbs up so that I hope you have actually understood it. Yeah, it need not. Okay, now whenever you want to find out the Euclidean distance, it will be integer values only guys, right? Yes, algorithm will also give more importance to high magnitude, because internally there are a lot of matrix multiplication, a lot of mathematical equations that are going on, right? And because of that, usually this is the scenario why we'll try to transform it, you know. Yeah, we'll discuss about normal distribution and everything, right? We'll discuss about log normal distribution, everything guys, don't worry. We'll discuss about Gaussian distribution and all the things. Okay, now this is the reason why you have to do the transformation. Now there are various kind of transformation, and remember guys, if someone asks you in an interview that whether transformation or scaling or standardization is required for each and every machine learning algorithm, you should say no. You should basically say some of the machine learning algorithms like linear regression, then you have some of the algorithms like logistic regression, then you have k nearest neighbor, where you have concepts of Euclidean distance like k means, hierarchical means, right? So all these kind of algorithms where Euclidean distance concept is used, or in linear regression, if you say that gradient descent concept is used, where you actually have to find out what is the global minima right? In all this kind of algorithms, you need to do standardization or scaling. Now this is with respect to machine learning algorithm. Now if I tell you, okay, do you require transformation in decision trees? Do you require transformation in random forest, or do you require transformation in XGBoost? Can you say what is the answer, guys? Do we require that or not? Do we require transformation in ensemble techniques where they specifically use decision trees? Just tell me one of this particular answer, guys. It will be pretty much important for you all to understand. Do we require transformation in ensemble techniques? I'll talk about deep learning very soon, but just tell me about this ensemble techniques. In ensemble techniques, internally, guys, you use decision trees. Decision tree splitting is happening based on the values. So you don't require transformation. You don't have to do min-max scaling or standard scaling techniques, right? In decision trees or in any ensemble techniques like random forest or XGBoost or AdaBoost, because internally decision trees create trees, right, based on the value. There you do transformation or there you don't do transformation, because always remember, transformation require some time. Okay, it required some amount of time, some amount of efforts is actually required to actually do that. And time is a very important constraint in actually solving machine learning algorithms, because if your model is able to give a quick result at that time, I think that is the best way we can actually do. Okay. Normalization, standardization used where we are using Euclidean distance. Not only Euclidean distance, guys, in this case also like linear regression and gradient descent, where they are actually finding gradient descent. In logistic regression also it is used, because there also we try to find out a best fit line, then we apply a sigmoid function on top of it, right? Now one more thing, what about deep learning techniques? So I'm just going to remove this. Okay, so deep learning techniques. So in deep learning techniques, many of the people will say ANN. Okay. Then the other technique is basically CNN. The third technique is basically RNN. So in all these techniques also you will be requiring transformation, guys. You will be requiring standardization. I can say standardization, right? Or you will be requiring scaling. Now why you basically have to do this? Okay, then over here you can remember, guys, in ANN, right, there is a concept of, again, global minima, right? Here also you have concepts of gradient descent. In all these three techniques you have all these things, right? In RNN, let it be LSTM, everything as such, right? So it can be anything as such. Okay, everywhere there will be scaling required, there will be transformation required. And if you have seen some of my examples, some of the live projects that I have done with image classification and ANN, there also I had done this particular transformation, right? In image classification, in CNN we specifically use a different kind of transformation. In CNN, what we do is that as we know, the images has pixels value between 0 to 255. So what we do is that each and every images has the value between 0 to 255 pixels. So each and every pixel, what we do is that we just divide it by 255, right? And that basically means we will try to transform the image pixels between 0 to 1. We will try to scale it down, scale down between 0 to 1. And that is what we do in CNN. In RNN and in ANN techniques, you can basically apply min-max scalar, or you can apply standard scalar, or any such thing, right? So in deep learning also, if someone asks you whether you require transformation or scaling or standardization, because this is one of the most important interview question, you should say basically yes. Yes, it does require. Okay. Now this all, I am just going to paste it over here. Always remember, I always have the habit of writing in this particular way, so that you will be able to understand, and you will develop a sense of understanding how you should basically learn a specific topic. Okay. Now in this techniques, first of all, there are various types. One is normalization and standardization. So this is basically the first technique. I'm going to discuss about this. In the second technique, I am going to discuss something like which is called as scaling to minimum and maximum, right? So I require this particular techniques too. In the third technique, minimum and maximum values. Okay. The third technique that I will be requiring, or I can say, is something called as scaling to median and quantiles. Okay, so this is the third technique. The fourth technique, I am actually going to discuss how a feature in the fourth technique, I'm just going to discuss about something called as Gaussian transformation. Now in Gaussian transformation, there are a lot of transformation, guys. Okay, so I'm just going to make quickly some of the points over here. First of all, we are going to discuss about logarithmic transformation. Just write it down, guys, along with me. So first of all, I'm just going to discuss about logarithmic transformation. Then I'm actually going to discuss about reciprocal transformation. Okay, and then we are actually going to discuss about square root transformation. So all this kind of transformation we are going to discuss, which will be pretty much amazing with some live examples, and then we will try to understand. And remember, guys, you cannot say that which is the best transformation. It completely depends on the data that you have. So this one I'm actually going to discuss about exponential transformation. And finally, you'll be able to see that the last thing that I'm going to discuss is about Box-Cox transformation. Okay, so all this transformation we will try to cover up, so that I think after this particular thing, I'm just going to write types of transformation. So after this particular class, you will be able to understand all the transformation whenever you require this, right? So this is what I'm going to discuss in this today's class, and probably we'll see till where we will be able to complete, and then we will try to focus on something else then. Okay, so this was right now we are going to start. Just give me a go ahead by giving this symbol so that I'll come to know that yes, you are ready. Okay. Impact on accuracy of scores in scaled versus non-scaled data. Usually it has been shown that if you scale your data, the accuracy, the performance usually increases. Okay, that is what it is basically shown. I'm just going to start it. Okay. Okay, guys, so I hope you all are ready. Will normalization have gradient descent settle fast? Yes, it will be definitely helpful. Okay, yes, it will actually help you to do a whole lot of things. So Ponsa Wellington says, Nayak, I'm doing a research on predictive policing. I want to use deep neural networks to predict a crime, but I don't know how to do it. Can you help? Can you tell me like what data set you are actually using? Then I'll just try to explore it. Okay. Okay, so the first technique that we are actually going to discuss is something called as standardization. So here I'm just going to write it down as standardization. Okay, now guys, always remember, if I talk about standardization, it is about transforming. I hope I'm written the formula correctly, right? So this is standardization. Let's see what is this spelling of standardization. Okay, standardization. So I've written it over here, I guess. Okay, something like this. Yeah, I've written in the same way. So if the spelling is wrong, just ignore it. Okay, so in standardization, what we do is that we try to we try to bring all the variables or features, okay, variables or features to a more to a similar scale. I can write, okay, to a similar scale, to a similar scale. Now what do I mean by scale? Oops, spelling mistake. Okay, to a similar scale. Now what do I mean by this similar scale? uh, that basically means, see, in short, I can also write standardization, right? If I write uh, standardization, I can also write like this. Standardization means centering the variable at 0. So 0 is basically considered as your mean, right? And we will try to bring um, or we'll try to transform all the variables considering the mean value is 0. Usually the formula that is basically given to this is something like this. It looks something like this. So we can write z is equal to, we can also use this as computing the z score. This will be nothing but x minus x underscore mean, right? I hope everybody knows this, divided by standard deviation. This is what is the basic formula for it, and this same formula will try to perform it with respect to our data set. Again, the data set that I'm actually going to use is something called as Titanic data set, guys. Over here I'm going to import pandas as pd, okay, and I'm going to say df is equal to pd dot read underscore csv, and then I am actually going to use something called as Titanic dataset.csv, right? And I'm going to say over here the columns that I'm going to use is basically all the integer columns I will probably be using. So first one is my p class, second one is basically my age class, the third one is basically my fair class, and finally I'll be taking my survived column, okay, survived column for computing this of finding out the transformation. If I go and see df.head, so I think it should get executed, and here it is, okay. So this is all my integer values that I'm going to take, and then I will try to perform some kind of transformation which will be pretty much important, and you'll be able to understand it, okay. So I hope everybody's clear till here. Yeah, mean of 0 and standard deviation as 1. Yes, perfect. And guys, if somebody has some kind of question, and if you know the answer, just try to help them out, so that because I'll be focusing on the class itself. So if you are actually facing any kind of problems, just try to ask someone over there. They'll try to answer you, okay. Let me just focus on the class, and probably that will help me to teach much more better, okay. So now I have all this particular information. Now what I'll do is that quickly, first of all, let me check whether there is any null values, or obviously there is some kind of null values. So what I'm going to do is that I'm just going to there's null values in age, so I'm just going to replace all the age values with basically the median mode, anything that you can use. So I will probably use median, df.age.median, okay, or median is this formula, median, yeah. And here I'm actually going to say in place is equal to true, right? And this is how I'm actually replacing. Now if I go and see is null dot sum, I will be able to see 0 null values, okay. So I have removed all the null values, because in age we usually have somewhere around 177 records as null values, okay. Now let us move towards standardization. So here, how do we perform standardization? Standardization is a very important technique, guys, which will actually, and this can be actually done with the help of a scalar library. So we use the standard scalar, okay, standard scalar from sklearn library, right? So this is the library we basically use. So in order to import it, if you don't know about standard scalar, from where it comes, just go and search in the Google about standard scalar. But here I'm just going to show you from which libraries you can basically import. So you can write from sklearn.preprocessing import standard scalar. So all the scaling libraries are present inside this pre-processing itself, pre-processing library itself. Now you can actually create your scalar variable and you can initialize to standard scalar. And always remember guys, this is basically creating an object of standard scalar. And then what we do is that I will just try to write df underscore scaled. So suppose this is my new variable, new data frame altogether. I want to scale all the values that are present in my df, right? So in order to do this, always remember guys, whenever you are applying a machine learning algorithm, you do only fit. Okay, so here I'm just going to tell you the basic difference between fit versus fit versus fit underscore transform, because here again you have a lot of question. This is also one of the favorite interviewer question. What is the exact difference between fit and fit underscore transform? Anybody who'd like to say what is the exact difference between fit versus fit underscore transform? Anybody? I'll just give you 10 seconds to 20 seconds time. You can go ahead, please. Anybody wants to tell the basic difference between fit and fit underscore transform? No one? Fit is nothing but fitting to the scalar. Okay, no one is interested, or you don't know guys. Come on. Okay, always remember one thing guys, with respect to machine learning algorithms, we only do the fit. Okay, we train our data with that. And suppose if you want to perform or change the data, at that time we have to use, basically apply algorithm and change the data. At that time I have to use transform also, right? So usually over here what is happening guys, the data transformation is actually happening, the variable transformation or the feature transformation is basically happening. So at that point of time what we do is that first of all we apply the object or the algorithm that we have taken, like standard scalar in this, and suppose this is responsible in transforming the variable, we have to use fit transform. So in this case what we do is that we quickly use something called as fit underscore transform, because here we need to transform our variable. So I'm just going to use fit underscore transform. Okay, and remember here I'm actually going to give my data set df. After that what I'm going to do is that I'm just going to execute it. And now if I go and see my df underscore scale dot head, now okay, it has an attribute. Okay, no head attribute at such, because when we do fit transform it will get converted between this particular value. Now remember guys, one important thing, if I just try to convert this into pd.data frame, then you will be able to see, okay, one very important thing. Okay, one very important thing like this. Now see guys, this first feature that you have, right, this first feature is nothing but is the feature equivalent to the survived column, right? And this first column feature is basically equivalent to p class. Then you have the second, that is this is equivalent to the h class, right? The transformation will basically be happening feature wise guys, not it will not be taking the row wise. Understand one thing, okay? So this formula that you see, that is x minus x underscore mean divided by standard deviation, this will be with respect to one whole feature itself. That whole feature, this particular feature, it will go and find out the mean of that particular feature. Okay, out of this whole feature mean, then it will also compute the standard deviation, and then it will try to apply x will be all values, like every record values will be actually treated as x of I, you can say, because it will be taking all the values from this particular records itself. So can I get a quick yes if you have understood how to perform standard scalar, so that I move ahead? Sumit Dalmia says, can you explain the difference again? See, fit and fit underscore transform is pretty much simple. Just imagine that if you want to transform your variables, okay, usually fit underscore transform comes along with any pre-processing libraries, because you need to change the data. Okay, and if you are using machine learning algorithms, at that time you will not be finding a lot of fit underscore transform, because machine learning algorithm will not be doing it. There are some machine learning algorithm like PCA, principal component analysis, it will be having fit underscore transform, right? Okay, can I get a quick high five, something like this? I hope you're understanding it, guys. I'll tell you when to use minmax, scalar, and standardization. Okay, we'll just try to find out both the difference. Okay, now what I'm going to do quickly is that, guys, I'm just going to do something like this. First of all, I'm just going to import matplotlib.pyplot as plt. I'm just going to do some kind of plotting thing. So matplotlib, then inline, right? Okay, I don't know why I'm getting this particular warning, but if I execute it once again, it goes off. I have to really check that out, and I really don't have time why I'm getting that kind of warning. So I will write df of scaled of, right? Now since df of scaled is an array, and suppose I really want to check the first index, or I want to really check which is the first index. First index is basically with respect to p class, right? So I will take all the records plus I'll just take the first index, and suppose I take my bins value as, I'm just trying to see in a histogram. So my histogram with respect to this value, see guys, 1 minus 1.566, if I go and compare, it is present in this particular values, right? So here are all my values, right? And here you can see that the variable looks something like this. Why it is looking like this? Just a second. Df underscore scaled, right? So this is the value, and I'm actually trying to take this. Where did the first value go? Okay, 216. Just a second, guys. I'm thinking I did something wrong over here. The transformation does not look like that. But if I consider this first variable, this is basically my column p class. Yeah, this is fine then. Okay, this is perfectly fine. So this is how my values got transformed. If you really want to check with respect to age, the age is basically my second feature. So I can also use this and use my second index. Now with respect to age, you can see that since we replace the missing value with mean, so you can find many values that is being in the center of this particular values, right? Similarly, if you go and check with respect to fair is in third index, right? So third index with respect to column, right? At that time you will be seeing that fair is little bit left skewed. There are very much less values at this particular region, but if you see with respect to this particular transformation, it is ranging between -1 till this particular value. Now since there is a lot of outliers in fair, the transformation is basically starting somewhere between -0.5 till this, because there are a lot of outliers. If there is an outliers, always remember guys, there will definitely be some impact in the transformation. Okay, so here we are actually seeing the histogram with respect to this. Can I get a quick yes if you're understanding? Type error, fit underscore transform missing one requirement. Okay, inside fit underscore transform you have to give one parameter, guys. Always remember that. The data frame you have to actually give. Data, okay. Yeah, no, that is not right skewed. Probably it is left skewed. This is left skewed. Okay, if you really want to compare, what you do is that just copy this. Okay, initially your original data frame, if I take with respect to fair, looks something like this. See this, it is left skewed only, 0 to this. We don't have any other values, right? Shiva Kumar, It's very, very simple. Fit underscore transform, just give that particular value over here. Let me remove this. Say fit underscore transform, just give the df value, store it in df underscore scaled. That's it. Sir, how do you know fair has a lot of outliers? Because you see this, right? This is left skewed, right? The original value is left skewed. So this 0 to this value is, a lot of values are actually present, right? Now here you can see that these values are present very high. So this is an outlier, right? It is whenever you don't find any Gaussian distributed. Now in this case, you have a bit of Gaussian distributed. The reason is that I replaced age with the mean, the missing nan values with the mean or median. Okay. How this is looking like right skewed, guys? It is left skewed, right? Right skewed basically means you'll be having a different diagram. You'll be having like this. See this. You'll be having something like this. Just a second. Let me just show you. You'll be having something like this. This is left skewed, right? Sorry, this is right skewed. Yeah. Okay. Yeah. So you are saying right. Yes. This kind of value is basically right skewed, guys. Okay. Left skewed basically means you can do something like this. Okay. Yeah, you are right. Sorry. I just got confused. Yeah, right skewed. Yeah, absolutely right. So again, I will be saying you how to draw this. So suppose this is your graph, okay? And probably if you make your diagram look like this is right skewed. If you make something like this is left skewed. Okay. Yeah. Sorry for that. I do make mistakes. That's fine. Okay. So here we have, and with respect to this, with respect to standardization, Shiva, just try it out. Everything is clear in front of you, right? What I did, I just replaced, I just did fit transform over here, right? So here you can see I've just taken this standard scalar and that just didn't fit transform on this particular df. If you're having some nan values inside your df, just try to replace that nan value with something else. Okay. So can I get a quick heads up? I hope you are able to understand. Hit the like button if you like this, and probably we'll be moving towards the next time. I think IQR scaling is better for this data. We'll see that. Don't worry. We will try to see each and everything. Don't worry, guys. Okay. Now the next scaling technique that I'm actually going to discuss is about min-max scaling. This scaling is also popularly used in CNN, right? So min-max scaling is most popularly used in CNNs and all. So this is also one of the most important scaling techniques and widely used in deep learning, right? The main aim, or I can say that this min-max scaling transforms the values, or I can say scales the values between 0 to 1. Okay, it transforms the values between 0 to 1, between 0 and 1. 0 to 1 also can be done, and 0 and 1. Okay. And if you really want to understand what is the simple formula for this is actually your formula. The formula basically says that x minus x dot minimum. So x is basically a feature. It will take each and every point, it will subtract with the minimum value, and then divided by x max minus x mean. So this is the usual formula that we actually used for performing min-max scale. Okay. Okay. How to decide between both of them? I'll tell you, Harsh, don't worry. Okay. I'll tell you which is the most common things if your data just imagine, right? This min-max scaling, as I told you, it works well with CNN. Okay, CNN in deep learning techniques. I will just write like this. In machine learning also people use this, but what they prefer is that they use standard scaling. Okay, because standard scaling helps you to find out the center median value, which is just like a Gaussian distribution, so it will definitely help you out. But if you have a kind of outliers, at that time it may get impacted somewhat. Okay, yes, for normal distribution we can definitely use standard scalar. Okay, let's go ahead and try to solve this. Okay, so it'll be again amazing for this. So for this, again I will write another library which is called as from sklearn.preprocessing. Okay, preprocessing. I'm going to import, there is a kind of min-max scalar. Yeah, min-max scalar. So here I'm going to say min underscore max is equal to, I will initialize min-max scalar, and then as usual, as I told you that, I'll just say df underscore min-max, like this data frame I'll create. And here what I'm going to just do simple is that I'll write pd dot data frame. I'll try to convert this into a data frame, and then with respect to this particular data frame, what I'll do is that I will try to take min-max dot fit underscore transform. Okay, and here I'm actually going to take df, and one more thing that I really want to write in this is that my columns is equal to df dot columns. Now what I'm doing, I'm just trying to convert this into data frame altogether. Okay, so if I go and see my df underscore min max, this is how it looks like. So I can also write something like df underscore min max, right? So I hope everybody is pretty much clear, right? Let me just execute it once again and just take the top 5 records. So here it is. Remember, each and every value will be converted into 0 to 1. Survived column need not be converted because the value is either 0 or 1. So here there will not be any kind of impact. It will be almost same. With respect to passenger class, you can see that it has got changed between 0 to 1. Age will also get changed between 0 to 1. Fare will also get changed between 0 to 1. Remember guys, in whenever you have a problem statement, as someone said in the live chat also, that if you have data with respect to standard normal distribution, just go and use standard scalar. If it is not following that kind of distribution, you can use min-max scaling, but most probably you have to use standard scalar. You know, it works pretty much well with most of the algorithms. Okay, so but in CNN kind of things where you have all the pixels between 0 to 255, you can actually divide that or use min-max scalar, divide by 255, right? It's pretty much simple. Okay, this is about this one. Okay, now let's go and see basically the distribution, how the distribution basically looks like. Again, what I'm going to do is that for distribution, I'll just going to write plot.hist, and here I'm actually going to take df min-max of any one column p, like p class, and here I'm actually going to take bins some value like 20. And now if you go and see in p class, you will be having this particular values because p class is a discrete values. Okay, so similarly if I go and check with respect to age, so df min-max age of bins is equal to 20. Here you can see that how it has got converted, and all the values has been transformed between 0 to 1. Okay, and similarly with respect to fares, this will also get converted between 0 to 1. Pretty much simple, right? So here it is all the values between 0 to 1. This value is basically an outlier, guys. This also actually you can consider this as an outlier, right? Okay, did you understand, everyone? Can I get a quick yes? Yeah, for decision trees, scaling is not required, guys. How did you identify outliers? As I told you, right? See this value. It is far away, right? If I try to again plot with respect to df of fair, I think you will be getting it somewhere here, right? Please go up. Where up? Just tell me the line, guys. I will be able to show you. So this is basically with respect to min-max scalar. Now the third technique that we are actually going to discuss is something called as robust scalar, which is pretty much important again. I'll come to outliers, don't worry, how to remove outliers and all. I'll come to that. We'll go step by step. We'll try to understand everything. Okay. Okay, can I get a like, something like that to go ahead once you all are done? Shall I go ahead? Or just give me 2 minutes time, guys. 1 minute time. I'll just fill my water bottle and come. Okay. Just give me 1 minute. Okay. So the third technique that we are actually going to see is something called as robust scalar. So here I'm going to write it as robust scalar, and I'm also going to tell you why do we use robust scalar. Okay. Robust scalar, it is used to scale the features to median and quantiles. Okay, this is what it is basically used, median and quantiles. Okay, so now what do I mean by scaling the feature to median and quantiles? It is very, very simple, guys. We actually find out the interquantile range. Okay, what is interquantile range? I'm just going to copy one description in front of you. Okay, and along with that the formula. So here you can see, let me make it as markdown. Okay, markdown. Okay, now robust scalar, it is used to scale the feature to median and quantiles. Scaling uses median and quantiles consist of subtracting the median to all the observation. Okay, subtracting the median to all the observation and then dividing by the interquantile difference. What is interquantile difference? It is nothing but the interquantile difference is the difference between 75 percentile and 25 percentile quantile. So this is the formula, guys. If you don't know about quantiles, just imagine when you have seen the box plot, there you will be getting 25 percentile, 50th percentile value, or 75 percentile value. Now if I give you an example of this one, see this. So if I have values like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now if I want to find out what is the quantile of 9, this 9 quantile over here is 90th percentile. Okay, 90th percentile. If you know about CAT exam, other type of GATE exams and all, they give you the percentage as percentiles. Over here 9 is 90 percentile. Okay, why it is called as 90 percentile? Because 90 percentage of all values in this feature, in this group, I'll say in this group is less than 9. This is why we call 9 as 90 percentile. Now if I take an example of 1, what is 1 then? 1 is basically 10 percentile value. 10 percentile value. Because 10 percentage of all the values in this group is less than 1. That is the reason why we call 1 as a 10 percentile. Okay. Now tell me, what is 4 percentile over here? What is this 4 value? How much percentile it will be? Just tell me this. Yeah, I'll share the notebook, guys. Don't worry. See, I'm preparing the notebook in front of you, right? So tell me, what is this 4 value? What percentile this particular 4 value is? Fortieth percentile? Yes, perfect. So 4 value is basically my 40th percentile. Okay. So over here, what we are doing, we are basically scaling the value based on this. First of all, I will try to find out the median value of that feature. Then I will subtract with x and then divided by IQR. IQR is nothing but 75 percentile minus 25 percentile. So if I try to find out 75 percentile, it should be somewhere around 7.5 minus 2.5. So 50 will basically be my value of IQR with respect to this particular distribution. So this is just one example what I have actually shown you. But now we will try to solve this with the help of coding, So let's go ahead, and for this, in order to do this, we basically use something called as from sklearn.preprocessing import robust scalar. And this I'm going to use a scalar which is equal to robust scalar, and here I am basically going to say that inside this particular scalar I'm going to say that okay, df of robust underscore scalar is equal to okay, scalar dot fit transform. Okay, and here I'm actually going to take the value of df, and probably I will do the same thing what I did with respect to transforming over here. I will convert this into a data frame, right? So here I'm going to basically replace by this. Okay, minmax. Instead of minmax, this will be my scalar dot fit transform df of columns. This is there, and then I will basically add df underscore robust dot scalar of head. So if I execute it, now you'll be able to see that all the transformation that will be happening based on this particular formula. Itself. Now again, you can also check, but I hope everybody is clear with respect to this. Okay, just give me a go ahead because I really need to check the distribution also. What is the difference between percentile and quantile? Usually what they do is that for the 75th percentile, they say this is basically a quantile. For 25 percentile, they say that it is another kind of quantile, right? So quantile basically means 25 quarter. Okay. Quantile 25 in 0 to 100. If I try to divide into 4, 25, 50, 75, these all are quantiles. Okay. Shall I go ahead, guys? Okay. Now the next step that I am actually going to, okay, Pathfinder, the name is Corey Schaffer. Okay. If you really want to see Flask and Django, he has actually clearly mentioned very nicely in his channel. Okay. Now the next thing that I will be doing, guys, is basically again calculating the bins and probably seeing how bins are actually looking at. So we'll first of all start with age. In age, again, we are getting that kind of distribution, And remember, the value will be between 0 to 1. That is with respect to the quantiles itself. Oh, sorry. This is df of robust scalar. I have to see in this particular way. So here the value is basically ranging between -2 to +4. Okay. Yeah, there are only 4 quantiles, guys. And with respect to fair also, I can actually check it out. Df of robust scalar with age. And here I'm going to check with respect to fair. And here again, it is, since it is having outliers, anyhow, the range values is ranging between minus something to more than 20. Okay. Why are we doing this? Because robust scaling also works well, because at the end we are actually trying to consider with respect to the outliers, right? So outliers over here is getting skipped. So we are trying to divide that thing. Let me just tell you why should we use this. This is amazing because a lot of advantages are actually there. Okay, guys, one more very important statement that they have actually given in this Wikipedia page, that the distribution of this variable is skewed. Okay, perhaps it is better to scale using mean and quantiles method, which is more robust to the presence of outliers. Okay, so that is the reason why they actually use this. It is more robust to the outliers. So it is basically said robust outlier. Okay, if I press shift tab, okay, there is an option like with centering, then you have quantile range, everything. See this? It's an amazing way to quickly do it, right? As usual. Can I get a go ahead so that I will continue the next important thing? Now the next important thing is with respect to something called as Gaussian transformation, guys. So now we are going to discuss about Gaussian transformation. So let me just copy that same thing that I had copied over here. So this is basically my Gaussian transformation. Okay. The first technique with respect to Gaussian transformation. Why do we use Gaussian transformation? Just a second. I'll just tell you. Very nice way of basically checking whether your distribution belongs to a Gaussian distributed or normal distributed or not. See, Gaussian distributed basically means normal distribution only. Okay. So always understand one thing, guys. What happens is that if your distribution is not normally distributed, so we can apply some mathematical equations on those kind of distribution and then convert that into a Gaussian distribution. Now, if I take this particular example of fair, right, this is, you saw that it is right skewed, right? Whereas if I take an example of age, this is normally distributed. Now, if this is not normally distributed, how can I convert that into normally distributed? So there are various techniques, So the first technique that I would like to suggest is something called as logarithmic distribution. Whenever we have this kind of skewed feature, we basically apply logarithmic transformation to basically convert this distribution into a normally distributed or Gaussian distributed. So this is called as Gaussian transformation. So the first technique that I am actually going to show you is something called as logarithmic distribution. Before that, let me just put all the sentence and what kind of problem statements we are actually looking at. So here in this, we are actually going to see logarithmic transformation, then we are going to see reciprocal transformation, square root transformation, exponential transformation, okay, and you also have something called as box transformation. So all these techniques we are actually going to see. I'll give you 2 seconds time, or not 2 seconds, 10 to 15 seconds time, please do write down this. Can we say standardization is a kind of Gaussian transformation? No, we cannot, because again, understand what is Gaussian transformation. What did I mention about it? I said that Gaussian transformation is nothing but, suppose your your variables, your features are not normally distributed, then we can apply some mathematical equation to convert that into a Gaussian distributed or normally distributed. And for that, we use Gaussian transformation. Why normal distribution is required? Because some of the algorithms, I'll say you guys, some of the algorithms like linear regression, logistic regression works pretty much well when your data is Gaussian distributed. Okay. So here I'm just going to say that some machine learning models, some machine learning algorithms like linear and logistic, right, assume that the features are normally distributed. Okay. So what we do is that in order to, and there are a lot of advantages with respect to normally distributed, right? And when we suppose they are some of the machine learning algorithms, they require all the features in normally distributed, they can perform well with respect to accuracy. They will give us very good result and accuracy and performance, right? So they will give us accuracy and performance. Now with respect to this, guys, why we require normal distributed? Because this algorithm will be able to work well and give us good performance. What if the data is not distributed? Then what we can do is that we can apply all these techniques to basically convert this particular data into a Gaussian distributed or normally distributed. That is what I'm actually trying to say. So can I get a quick yes so that I start this particular explanation, guys? Some or all models except trees. So if I talk about this, decision trees does not require this. Whereas in machine learning algorithms like linear regression, logistic regression, if I talk about some more algorithms like probably KNN also works well with respect to this. Again, you can Google and search which all algorithm Gaussian requires data to be normally distributed. Okay. After log transformation, do we need to apply normalization? No, okay. Do you need to apply normalization? Yes, probably it may require. Okay. But we'll just see how to basically perform this. Now let me just read a data set again. So I'm just going to write pd.read_csv, and here I'm actually going to take data set of titanic.csv, and probably I'm going to use columns, and here I'm going to take three features. One is age, fair, and then I'm actually going to take survived. Okay. So if I go and write df.head, so this is basically my feature. On this, I will try to see whether my data set is basically, is it Gaussian distributed. If it is not Gaussian distributed, then we'll try to do some kind of transformation. Okay. So first of all, what I'm going to do quickly is that, guys, I'm going to replace this age with something else. Okay, with the median or something else. Okay, so for that, I'm just going to fill the nan values. So here I'm going to say fill nan. So here I can write df of age. Okay, is equal to df of age. Okay, dot fill na with df of age of median. Okay, median, why I'm using it? Because it will actually help me to reduce the outliers, right? So if I go and write df.head, you'll be able to see that whether I'm having any null values or not. So I can write is null dot sum, and here, oops, there is some syntax error. Okay, if I go and see, there is 0 null values. Now quickly, what I'm going to do is that I'm going to create some two plots. Okay, so first let me define a function. Always remember, guys, if I want to check, if you want to check whether feature is Gaussian or normal distributed, what technique we use? Someone can say we use something called as QQ plot. QQ plot. This is a pretty famous plot which helps us to check whether a data is Gaussian distributed or normal distributed. Okay, we will try to use something called as QQ plot. Log transformation is also a type of scaling. Yes, yes. We'll just see how the values will be. I think you don't have to do normalization again once you apply that. Okay. Harsh Arora, you are right. QQ plot. Okay. Now let's see how do we perform QQ plot. Now in QQ plot, right now with respect to this, QQ plot is all about plotting. Okay, is about how you plot the data, and if that plot satisfies some condition, then you can basically say that yes, this is pretty much good, and we can say that yes, it actually follows a normal or Gaussian distribution. So first of all, what I'm going to do is that I'm just going to say plot underscore data. Okay, and here I'm going to take my first variable as df, and then second variable I can take it as my feature. Okay, now this feature, what I'm going to basically do is that I'm just going to say plot dot figure. Remember guys, this is a simple plotting technique. So I'll say fig size is equal to 10,6. Okay, so I'm going to basically plot this, and here I'm going to plot two diagrams, one on the left, one on the right. Okay, on the left will be my distribution in histogram. On the right, it will basically draw a QQ plot. Okay, so like this I'm actually going to do. So for that, I'm going to use something like plt.subplot. Okay, and then here I will take that. Okay, I require 1 row, 2 columns, and this will be for my first index. Okay, and then I will plot this particular feature. Whatever feature I'm saying, I'm just going to plot the histogram for this. Okay, so this is what I'm doing. Whatever in the left hand diagram, I am just plotting the distribution of the feature. Okay, now in the second diagram, what I'll do is that I will try to plot something else. So plt dot subplot. Okay, now this will be my first row, second column, second index, right? First row, second column, and second index, right? So here I'm actually going to say, and before this guys, if you really want to apply QQ plot, there will be a library which you need to import, and for that I will be importing a library saying that import SkyPy. Okay, it is basically a SkyPy library. So I'll say import SkyPy, okay, dot stats as stat. Okay, so I'm going to use this particular library, and this particular library will be helpful for constructing the QQ plot. Okay, now inside the stats, what I have to do is that there's a function which is called as prop plot. There's something called as prop plot, I guess. Prop plot, PLOT plot. Okay, if I press shift tab, I'm not able to see why. Oh, it is stats. Okay, stat dot prop plot. The first variable that I have to give for which variable I want to see whether the QQ plot is working fine or not. So I'll write df of this feature, and then sorry, this should be not in string. Okay, so df of feature, comma, okay, the distribution technique that I have to use is something called as normalization, norm techniques. Okay, so and this will be plot is equal to pylab. Okay, so all these things I have actually discussed in my previous videos and all guys, and probably pylab is also one more library which you need to import. So I'm just going to import this pylab over here, which will actually help you to plot this. This is just fixed guys, a kind of syntax which you will be commonly using. And then finally I'll say plot.show. Again, remember what is this prop plot? Let's see, shift tab. Here the first parameter I give the x value, which is my feature. Distribution is norm. So what is this distribution? It is nothing but distribution or distribution function name. The default is norm for a normal probability plot. So what it is going to do, understand one thing. This will be my x-axis value. Okay, this will basically be my x-axis value. And we probably need a y-axis value because we will try to plot x and y. Okay, and then we will see whether all the points fall in a straight line or not. So in the y-axis, we basically use a normally distributed data which gets initialized by this particular function. Okay, so that y data will be plotted in your in your x-axis. In your y-axis, you will basically be having that particular feature. I'll just show you how it looks like. So I have my df of feature over here. And then I've actually done plot.show. So once I execute this guys, you'll be able to see that. Let me apply this plotting thing on my age variable. Okay, so here I'm going to basically say df comma age, and if I go and see, okay, there is an error, module object is not subscriptable. Okay, plt of, Oh, did I make a mistake? I have to write df of, oh, sorry, I wrote plt. I don't know why. df of, okay. So df of age. So here it is. Now here you can see that, guys, age is basically distributed in this particular way. Okay. Age is basically distributed in this Gaussian distributed way. And in the right hand side, you see that this x value is basically your age after doing this. And then you will be seeing that you will be seeing this theoretical quantiles. So this is the normally distributed data that has been initialized. Okay. And these are all your points. So both are mapped. And if they are actually falling in the straight line, then we can say that age is normally distributed or Gaussian distributed. Okay. Always remember this thing. So if this all points are falling in the straight line, we can say age is Gaussian distributed. Is everyone clear from that, guys? Any queries? Yeah, I'm sorry, Madhukant Dinkar. I was just writing this. Okay, so I missed it. So here you can see that all the points are mostly falling in the same line. But still, can we do some kind of transformation and check whether this, whatever I'm actually saying, is probably correct or not? So the first technique I'm going to basically use is something called as logarithmic transformation. And we are also trying to transform it and check whether whatever I said is properly fine or not. Okay. So in logarithmic transformation, what we do is that, guys, we basically use a very simple thing, that is, I'll create a new feature, df of age underscore log, and here I am basically going to say that np, oh okay, I have to import numpy also. So basically import numpy as np, because I'm going to use some techniques of log. So I'm going to write np.log, and here I am going to give my, I have to apply this logarithmic on what? On my age. Okay, age variable. Then I am also going to plot the data, and here I am actually going to give my df comma my another feature, which is age underscore log. So once I execute this, guys, you will be okay. Df, not data, df. Okay. So once I execute this, you can see that, guys, after applying logarithmic transformation, it is not falling in the straight line. So definitely I cannot use logarithmic transformation to make it Gaussian distributed. So this is not that suitable. But what if I try out my next technique? Okay. So can I get a quick yes, guys, if you are understanding everything till here? Saurav Tiwari says this is not QQ plot. Which is not QQ plot? This is the QQ plot, right hand side. Okay. So can I get a quick yes if you are able to understand all these things, guys? Right? See, guys, QQ plot is the combination of whatever age values you have. You will be having that in your y-axis. In your x-axis, you will basically be creating this theoretical quantiles. So this is all normally distributed data that gets initialized. Okay. Now, when you are actually trying to check this observed values, this is the real values. Okay. This real values that is present in your age. Okay. Once you check with this, it should fall in the straight line. Now in logarithmic, what I did is that I just tried to find out the log of this particular age. That is why it is called as logarithmic. Okay. And always remember, guys, logarithmic will work well when your data is rightly skewed or left skewed. Okay. In that scenario, it will convert that skewed data into Gaussian distributed. We'll just see for fair. Okay. Just a second. Just give me a moment. We'll check for fair. So suppose if I go and check for fair log. Okay, df of fair log. If you remember, guys, if I go and plot fair, if I go and check for fair, right, I'm just going to try to plot fair. Okay, in fair, we have seen that it is not, it is right skewed, right? So if I go and see fair, you can see that this is right skewed. And over here, the QQ plot is basically not falling all on the straight points. Now what I'll do is that for this particular fair, I will try to apply a log normal distribution. something like this, and then I will basically be plotting this fair log. So once I execute this, you will be okay. It is giving me some error. Why? Let's see the error. Does fair has some values like zeros? Why it is giving me this error? Okay, let me just see whether the error is actually present in this or the below thing. Okay, I'm getting all the values like this. It is fine. Df of fair underscore log. Why is there an error? Probably. Yeah, we can use other transformation also, guys. Okay, guys, I'll come to fair. Okay, just give me a moment. I'll come to fair first. Let's check which transformation is good for age. Okay, I'll just come to that. Okay, why we are getting that error? I'll just check it out. Okay, right now in this particular session only. Now I'll remove this fair also. Fair is not required right now. We'll just check with respect to age. Now the next transformation that we are actually going to see is something called as reciprocal transformation. Okay, so here I am going to see reciprocal transformation. And in reciprocal transformation, again guys, what we are going to do is that it is pretty much simple. I will take df of I'll create a new variable like age underscore reciprocal. Okay, reciprocal is nothing but reverse. Okay, so I'll write 1 by df dot age. Okay, and here I'm actually going to say plot underscore data, and here I'm going to give my df, and the variable that I'm going to give is basically age reciprocal, age underscore reciprocal. Now once I plot it, you will be able to see that yes, this is also not following in the right thing. If I do the inverse, it is becoming right skewed. Okay, and after reciprocal, reciprocal is nothing but 1 divided by that particular values. Okay, there is also a transformation which is called as square root transformation. So different transformation is there, guys. Square root transformation. Okay, now in square root transformation, again what we do is that we take data of data or df of I will just write it down as age underscore square. Okay, or I'll just say age underscore square. Okay, square. Okay, fine, is equal to, now remember in square root we are just going to find out the root of the age value. So I'll write df of age, and if I really want to find out what is the root of this, I can just write like this, to the power of 1 by 2, to the power of 1 by 2. So like this we can actually find out the square root of a value. So I'm going to plot this, plot underscore data. Here I'm going to give my df value, and my variable is something called as age underscore square. So if I go and check again in this also, I am getting some error, key error, it's age square. Why? Age, oh sorry, I made some spelling mistake. Okay, so once I do this, here you will be able to see that again it is trying to get followed in the same line, and it looks pretty much amazing, right? So here is how the square root transformation is looking like. Is everyone clear? I'll just check, guys, why log of 0 is not defined, it is coming. I'll just check it. Okay, please explain x-axis in the left plot. This is pretty much simple, right? If you don't know about probability density function, histograms, just check out my videos, guys. Okay, I'll also be discussing about box cross transform. Okay, now the next transformation that I will be doing is something called as exponential transformation. Exponential transformation, right? So in exponential transformation, again I'll write df of age underscore exponential is equal to data. Exponential basically means what, guys? If e to the power of something, right? E to the power exponential. Okay, let me just Google it. How to write exponential in maths Python, right? Exponential exponential in Python, how to compute it. So it looks something like this. Exponent is nothing but 3 to the power of 4. This is the base 1, right? So probably if I really want to find out the exponential, it is basically equal to 2.718. Okay, here what I'm going to do is that I'm just going to say df of dot h multiplied by or to the power of 1 divided by 1.2, right? This is what mathematically e to the power of that value will actually give you. So I'm going to use this. Okay, you can vary the exponent as needed. It is up to us. Okay, so once I do plot underscore data, and if I go and give my df comma age underscore, I'll just copy this, age underscore exponential, you will be able to see that I'm actually getting this particular value. And this is pretty much good, right? When compared to this one, that is normal distribution over here, this looks pretty much good because most of the points are actually following into this, right? So this is basically the formula for applying the exponential transformation, guys. There is also one more technique which is called as Box-Cox transform. Now just please keep a note of this and just try to explore how the exponential formula is derived, because this is what I got from the Wikipedia itself. And probably I'll be using this particular formula to find out the exponential transformation. Now there is also something called as Box-Cox transform. So this is probably the last one on the transformation, Box-Cox transformation, right? So Box-Cox transformation, I'm just going to keep it as a markdown because this is also a very important one. Now remember guys, if I write stats dot, the Box-Cox transform is basically present inside this imported library that I have imported with respect to that. Okay, so here you have something like as Box-Cox, and inside this you just provide your feature. So I'm just going to say df of age. If I execute this, guys, this gives us some values, some important values. Some of the values are basically, I'll tell you what all values you will be actually getting. One is the transformation of the Box-Cox age. So age underscore Box-Cox. I'll also tell you what is the formula of it, guys. Don't worry. So Box-Cox, okay, and the another value that you will be getting is something called as param. Okay, any kind of parameter. So I'll just say parameters over here. I'll discuss about this formula, guys, and let me just tell what is the formula for Box-Cox. So the Box-Cox transformation is defined by this particular formula, which you will be seeing in your explanation, guys. I've taken this from Wikipedia. So here we have y exponential of lambda. I'll tell you what this lambda is. Lambda is nothing but whatever this parameter value you'll be getting from this particular function is lambda. And then you have y is nothing but your normal age values, where y is the response variable and lambda is the transformation parameter. Lambda varies from -5 to +5. In the transformation, all values of lambda are considered and the optimal value for a given variable is selected. Okay, so once we do this, we can also print our lambda value. So here you will be seeing, if I print parameters, okay, you'll be seeing all the values are between -5 to +5 only. Okay, so this is basically my parameter, and this is selected based on this particular feature, that is age. It has a lot of maths to be dealt in between, guys, to understand what is Box-Cox transformation, and probably I'll do that in my another video. But really this one's all about, I really wanted to show how the transformation actually works. So here we will be focusing on how we can apply Box-Cox transform. So here I'm going to take this age and basically check over here and press shift enter. Now this is also looking pretty much good, and this has actually converted into a much better than exponential format. And reason is that it has basically applied this particular formula. I know people will not be able to understand the maths because it has a lot of maths to discuss with respect to Box-Cox transform. So by using Box-Cox transform also, we can actually convert that into a Gaussian distribution. So yes, this was in short about the videos, today's class. So in real time, we always transform like this for all columns. Yeah, we need to check whether, suppose if we are trying to apply a linear regression, ridge regression, lasso regression, at that time obviously it will require all the features in Gaussian distributed, and it is always good by just writing one for loop you can check all the Gaussian distributed data or not. Based on that you will be able to see this. Okay. Narendra Prasad is saying, sir, I'm doing dislike. Please go ahead, not a problem. Right. So in this video, what we have done is that we have basically understood all this transformation. Okay, all this transformation. The main important transformation, as we saw, is in normalization, standardization. We saw scaling to minimum values, scaling to median quantiles. Then we saw Gaussian transformation, in which we saw logarithmic transformation, reciprocal transformation, square root transformation, exponential transformation, Fair-Cox transformation. Yes, fair has 0 value. So because of that log of 0, it was giving us error. So what I can do is that, let's see for fair, how do we fix it? We can remove that values, which is actually having 0. Okay. Which is actually having 0. We can actually remove that. Sir, in real time, we explore all transformation like this. Yes, it is always good to check this kind of transformation. This is usually done in the exploratory data analysis. Does ANN require normalization? Yes, obviously ANN also require normalization, guys. Yeah. Okay. Please show the last code. Here you have the whole last code. Yeah, this is the syntax. Please don't forget the parameter. Okay, guys. If the fair is having 0 value, probably we can replace with something else. Okay, just try to see whether that value is coming as 0. How do we can skip that particular value. If we skip that particular value, how to skip that particular value? When I am actually trying to see, probably I'll try to replace that 0 with something else. Yeah. Just try it for df, guys, and wherever you are getting that 0 value, just try to delete it. How to choose the best fit method? Whichever is following a proper. Now, out of this, what do you think, guys? Which transformation I should apply on age? Out of all these things, what transformation should I apply? See, my transformation technique, what I will do is that according to this, I will either go without any transformation, because this is following almost in the straight line. And then I will probably go with this one or this one. But I think this is pretty much better. Okay, exponential. But if I go and see Box-Cox also, it is pretty much better. Use log of 1p for fair. Yes, let's try. Okay, now I'm just going to do it for fair transformation. Okay. Now in fair, the first case is logarithmic. In logarithmic, what I'll do is that I'll write df of fair underscore log. Okay. And here I will basically use np.log 1p. Okay, so log 1p is also there, which someone has said. Thank you for that. And if I write df of fair, I will probably be able to get this. Now I will just write plot underscore data. Okay. Here I'm actually going to give something like this, plot underscore data. The parameter that I'll give is df, and this will basically be my fair underscore log. Now, fair underscore log. So whenever you have that kind of scenario, please replace it with 1p. Now see, guys, this is pretty much amazing, right? If I go and see my fair plot, right? First of all, if I go and see my fair plot, you'll be seeing that fair is right skewed, right? But this kind of problems can be pretty much fixed by using logarithmic transformation. Okay. So what is log 1p? Just Google it, guys. Just Google it. Log 1p. Log 1p versus log. The log function computes the value of natural logarithmic of argument x. The log 10 function computes base 10. the log function computes the value of log 1 plus accurately even for tiny argument x. So whenever you are trying to find out log 1, it will basically be computing for log 2. So at that time, you will not get that error of log 0. Okay. Log 1 is basically like that we are actually trying to solve. Now, one important thing with respect to this, guys, over here you can see that this is right skewed. When I applied logarithmic transformation, it is falling into the same line in QQ plot. So basically, you can solve this particular problem with respect to this. Let me try some other transformation like box-cox. I really want to see how box-cox will perform with respect to fair because it is rightly skewed. Okay, so here I'm actually going to do this, and here I'm going to write fair. Okay, here I have all the values, and then after this I am going to basically plot this particular data, and for plotting it, df of fair underscore box-cox. Okay, here also probably I'm getting some error. Data must be positive values. Okay, we are getting negative values, I guess, for this. Let me just check. Let me just check in my practice material. Probably it will be able to understand then. Okay, now for this also I will be using +1. Okay, guys. Now here you can see that this is also an amazing transformation that we have actually done. Whenever you get that kind of error, guys, just do +1 over here so that you will be able to do a box-cox transformation, because probably we are getting a negative value after doing the box-cox transformation. Okay. So just try with respect to all the others, like logarithmic I have tried, reciprocal just try. For right skewed, according to me, guys, the best will be logarithmic one. Okay, which will be best will be logarithmic one. For logarithmic, you can also use you can basically use np log. Suppose you don't want to use np 1p, just use np log +1. You can do +1 also. And once you execute it, you will be able to see this. Okay, you can also use +1 over here, so that whenever you find log 0, at that time that situation is getting handled. Okay. Now probably I will just upload this particular materials to all of you guys. This which is pretty much important. I am just going to upload this materials so that you can check it out. Just give me a second. Live streaming, feature engineering, missing values. Let me rename this feature engineering, normalization and all, day 6. I am just going to upload it over here, and you can actually try it out. Thank you, guys. People are saying excellent session. Thank you. Okay, guys, just do one thing now. Just reload the page, and probably you'll be able to see the GitHub link in the description of this particular video, and you can download the materials for today's session. Okay. And remember, in the previous session, which I had actually discussed about one more thing, which is called as probability ratio encoding, that also I have actually uploaded over there. Okay. So please just reload the page and just try to see it. Once you're able to get it, just give a like button or something. Just give me this symbol so that I'll be able to understand whether you have got the files or not. Okay. So which should be done first, standardization, scaling, or transformation? First of all, go and check whether your data is normally distributed or not. If it is normally distributed, just go with standardization. Otherwise, go with transformation. Okay. Guys, just reload the page and just go and click on the GitHub link. You will be able to see that. Narendra Prasad is saying, I have told you that I want to dislike. Yes, please go ahead and dislike. Not a problem. Okay. Yep. Okay, guys. So just reload the page. Just tell me whether you are able to see the materials or not. First of all, just tell me that. Thank you, Sumit. Thank you. please share Q&A channel. Guys, I've given my Discord server link in the description of this particular video, Telegram link in the description of this particular video, GitHub, everything has been given. My another channel link is also given. Every information is given in the description. So is transformation used for discrete or discrete or continuous and encoded? It can be applied to discrete also. We saw, right? P class, that is passenger class, it is basically discrete. Okay. So hit the like button, guys, if you like this particular session. And yes, tomorrow we will start with feature scaling. And please make sure that I'm also being uploading PyTorch videos in my another playlist. So today one more video on PyTorch is going to come. I was just preparing everything as such for those. And if you like this particular video, hit like, share with all your friends, guys. And yes, I'll see you all in the next video. Please download the materials. And yes, guys, thank you for attending this session. I hope you liked it, and we will be continuing this kind of sessions again and again. No, BERT is not yet discussed. BERT requires a lot of understanding. There is a lot of theoretical understanding. See, if I show you the practical implementation, you'll not be able to understand BERT. Theoretical understanding is pretty much required in that too. Okay. So thank you, guys, for attending this particular session. And tomorrow probably I'll be coming around 7 or 7:30 p.m. and we will be continuing the feature selection. Okay, so I hope you like it. We did amazing things in feature engineering with respect to this, and probably now it is time. What I'll do is that I'll also try to see with respect to outliers. Tomorrow we'll try to see how we can treat outliers, how we can fix outliers and all, and then we will move to feature selection. Tomorrow timing either 7 o'clock or 7:30 p.m. guys, any one of them. Thank you, guys. Bye bye. Have a great day ahead. And yes, okay, I'll make a video on boxcox also. Okay, thank you. So everyone, I'll see you all tomorrow. Bye bye.